Alright, hey you guys, we're back to defining rigid transformations. I'm on page 10, which is called reflections. So one more time, a rigid transformation is any kind of rotation, reflection, or translation of a pre-image, which is your original figure, to a new position. That's called the image. You can do a combo of those. You just can't do a dilation. So you can't make it increase or decrease in size, like an enlargement or a reduction, because that is not considered a rigid transformation. So what I mean by combo is we've talked about rotations. You can do a rotation then a reflection, or a reflection then a rotation, and throw a translation in there. Anything except make it enlarge or make it reduce in size. Okay, so let's get going. Looks like I have a GeoGebra. You will pretty much always have a GeoGebra. Alright, let's see what we got here. Let me move this so I can see what's going on. Alright, so I definitely have some sort of, well, it looks like a trapezoid, to be honest with you. This is my original, because it's just regular ABCD. This is my new figure. That's my image, because it has subs by the A's, the B's, C's, and D's. This is my line of reflection. Line of symmetry, pretty much the same thing type thing. Alright, so let's see what's going on. What have I got to do? Alright, so polygon ABCD has reflected across line GH to give polygon A prime, B prime, C prime, D prime. Change the line of reflection. You can move each endpoint individually or move the entire line. As you move the line of reflection, what do you observe about the relationship between polygon and its image? Alright, so there's my move. It's already there. Alright, so if I move it, so if my polygon gets further away from the line of reflection, then my new polygon will also be further away. The closer it gets on the pre-image, the closer it gets on the image. If I have it touch, then naturally it's going to touch the image. They are the same distance away. So I'm going to say the distance of the pre-image to the line GH is the same as the reflected image. Seems like we talked about that before. Distance is the same. Question 2. Be sure that polygon ABCD is not touching its image. Okay, did I leave it? No, I left it on my part. Good deal. All right, draw a line segment connecting A to A of GH. All right, so they want us to draw a line segment. So I'm going to come over here to line segment and connect A to A of H. Notice that A of GH intersects the line of reflection GH. Mark the point of intersection. So I'm going to come over here to point. I'm going to put a point where they intersect. It's a little off. Let me undo it. Okay. Oh, there we go. See how it's turned black? I know there's my point of intersection. Okay. Measure and record the angle at the intersection. All right. So to measure an angle, we're going to go to my angle icon. And remember, anytime you do an angle in GeoGebra, you have to do it in a clockwise motion. You have to go this way, like a clock. If you go the opposite way, sometimes it gives you the wrong angle. So I just clicked on A, F, and G. And it looks like I have a 90-degree angle. All right, what happens if you move the line of reflection? All right, well, I'm going to come over here to move. I'm going to grab my line of reflection. Looks like my angle remains 90 no matter what. Even if I try to go up and down, it still says 90. So the angle is 90 degrees and remains 90 degrees when the line of reflection is moved. Okay. Question 3. Measure and record the length of A to A of GH. Well, The nice thing about that is that GeoGebra gives it to us. It's 4.98 as my figure is right now. Now, if I move my line of reflection, of course, that can change. I mean, look, now it's 3.87. So I'd like to get it on a nice number. Let's see. All right. Oh, I'm on 4. Let's go with that. All right. Then measure and record the distance between A and the point of intersection you created. Do the same between A of GH and the same intersection. Well, here's the deal. If the entire thing is 4, and remember they are the same distance away from the line of reflection, then all you got to do is say 4 cut in half would be 2 on the left and 2 on the right. To prove it, I'm going to come up here to my angle symbol. Instead of selecting angle, I'm going to select distance and length. And I'm going to click on A to the intersection, and I get a 2. And I'm going to have to move that out of my way, aren't I? And click this again. A to the intersection, also a 2. So for my visual people, I just proved that they are the same distance away from the line of reflection. So if the whole thing from A to the new A is 4, half on the left is 2, half on the right is 2. All right, so looks like I just got to fill in the table. So I had a 4, 2 on the left, 2 on the right. All right, well, let's see. Let's make it a 5. Do these move? Oh, look at that. Okay, so I'm going to change this to a 5. If I can get it to stick on there. I got 5.02 and 4.98. It doesn't want to be nice and land on a 5. But if it was 5, what do you think it'd be on the left and right? Well, it'd be half. Half of 5 is 2.5. So it'd be 2.5 on the left and 2.5 on the right. So let's go with 5. 2.5 on the left, 2.5 on the right. If it was a 6, what do you think it'd be on the left? That's right, it'd be half. 3 on the left, 3 on the right. To make my life easier. Once you understand, you can go ahead and complete the table instead of having to shuffle back and forth all the time. Okay, so question 4. Repeat question 2 and question 3 for corresponding points B and B of, okay, C, because we're doing all of them. Okay. All right. With your measurement displayed in GeoGebra, move the line of reflection around the coordinate plane. Also move the points of pre-image if you like. Based on your investigation, what can you conclude about the line of reflection with respect to the image and the pre-image? Okay, so basically, the distance is always the same. The angle will always be 90. But for you visual people, let's take a look at this. So I'm going to draw a segment, B to the new B. You won't be able to see C very well because you're just going to cross over D. So let me do D. The angle will always, oh, I forgot my point. Let me put a point there at the intersection. Point at the intersection. Point at the intersection. Mark my angle. I guarantee it's going to be 90. Look at that. Bam, 90. And D, J, F, bam, 90. So the angle is always going to be 90. I'll come over here and hit move, and I'll move this. And you can see that it doesn't change. They wanted me to do my distance. So distance, I've already done A. So how about B to the intersection? And the intersection to the old B. So they're cut in half. D to the intersection into the original, and it's also been cut in half. So if I move it, whoa, let me come back to move. So if I move my line of reflection, you'll notice they always stay equal to each other. So for my visual people, there you go. It does not change if you're looking from A to the new A or B to the new B, D to the new D. The distance is always going to be the same. The angle is always going to be 90. The distance remains the same on both sides of the line of reflection, and the angle will remain 90 degrees. So no matter where it is on your figure. Okay, question 5. It's time to verify that a reflection is a rigid transformation. You'll begin with the angle measurements. Measure the angles of polygon ABCD and the angles of the reflected image. Record the measure of each angle to the nearest degree. So we're basically proving that the angle measures don't change. All right, you know what? I'm going to get rid of all this because it's busy. So I'm going to undo. All right, let me get back to my original figure just so it's kind of nice and prettier. Okay, so we're going to find these angle measures and compare them to the angle measures of the reflected image. Well, to be a rigid transformation, it can't be a dilation. So my angles are going to remain the same. But just to prove it, I'm going to go to my angle. And remember, when you do angles, it has to be in a clockwise motion. So I'm going to click on D, A, B, which is 90. A, B, C, which is also 90. B, C, D, 45, C, D, A, 135. All right, again, clockwise motion. So DCB, there's my 45. It matched up with my original C. CBA, 90. So my new B is also 90 for my old B. BAD, also 90. So my A's match up. Last one, A, D, C. Looking for a 135, and I get a 135. So I'm just going to put those into my answer box. Remember, it's the angle in the middle. That's your vertex, the one you're actually talking about. So we found B to be 90, and the new B is 90. C is the letter in the middle, which was 45, and the new C, that's the image, is 45. D is the letter in the middle. D was 135, and the image D is 135. A was, what was A? A was also 90, and that means the new A is also 90. So they're not going to change each other. All right, sweet, there we go. All right, looks like question 6, looking at line segments this time. All right, so we're going to look and see if the line segments enlarge or are a reduction. Well, and I'll tell you right now, if it's a rigid motion or a rigid transformation, they're not going to change. They're going to be the exact same. So let's go back here. Gosh, it's busy. Let me get rid of all this so we can see. All right, much better. So I'm looking for the distances of these. So instead of clicking on angle and keeping it on angle, I'm going to go to distance or length. So AB. Oh, undo. Let me mix that up. I thought I was looking at that point. All right, 1.41. AB over here. Keeps giving me the wrong thing. Let me do this better. So I'm going to click the dots. A to B, 1.41. A to B, 1.41. Okay, there we go. That's better. All right, so let's see. B to C, 2.83. B to C, 2.83. All right, C to D, 2. C to D should also be a 2. A to D is 1.41. And that sucker's in my way, so I'm going to have to move it out of my way. Go back. A to D, it should be 1.41. Yeah, there we go. So they are the same, which means it has not been dilated, hasn't increased or reduced. So we're good to go. So AB was 1.41. The new AB, 1.41. The original BC was 2.89. The image, 2.89. All right, CD, again, that's the pre-image was 2. The image was 2. AD, the pre-image was 1.41. And the image is 1.41. So they didn't change in size, you guys. This is most definitely a rigid transformation or a rigid motion. All right, question 7. How do the angle measures of polygon ABCD compare to the angle measures in the reflected image? Well, they were the same. How do the side lengths compare? They were the same. What can you say about the preservation of the angle measures and the side lengths of a shape during a reflection? Well, this means it is a rigid transformation because nothing changed. The measures stayed the same. Measures remained the same over the line of reflection, which means this is a rigid transformation. Sometimes called a rigid motion, just so you're aware. You'll hear me say both, rigid transformation, rigid motion. I've been teaching geometry over 20 years, so I'm going to say rigid motion most of the time. I'm using the word rigid transformation for Edmentum because that's what they use for Edmentum, but it's a rigid motion. All right, so self-evaluation. Like I say, I know my geometry. All right, I'm going to hit submit, you guys. I think we got one more in this lesson, defining rigid transformations. So I will see you one more time before we go to the next lesson.